Okay, great. Yeah. Oh, so thanks Prahladh for and the organizers Irit and Venkat for organizing this. Thanks to the ICTS for having. Yeah, it's a really great setup. I have very yes. Yeah, I'm very impressed by how nice and modern everything looks, and yeah, I'm really looking forward to a great week. Great 2 weeks, in fact. So I'll be talking about error correcting code. So Mrinal and I will be talking about a bunch of topics. We're alternating our lectures. There have been a lot of recent advances in error correcting codes using ideas from algebra, using ideas from combinatorics, expanders, things like this. And hopefully by the end of the week, you would have seen a lot of things that happened here. So I'm going to just dive right in. So that board, so I won't reach that for a while, but okay, great. So I'm going to start off with some very simple definitions. This lecture we'll just see some of the words that we'll be playing with over the week. Great. So let's start. Sigma is going to be a finite set, and it's going to be called. It's going to be our alphabet. And the space which we'll work in is sigma to the n. And what's n? N is this quantity that it'll always be going to infinity, and all asymptotics are in n going to infinity. And a good example of a finite set is 0, 1, and we will keep that in mind. And there will also be settings where we'll talk about sigma being growing as n changes. So sigma changes as n grows. That's a more complicated thing to visualize, but we'll keep that in mind. And when we actually do such things, I will say more about what it means. So this is our setting. And sigma to the n it comes with a natural metric, the Hamming metric. Where the distance between two strings x and y is the number of coordinates where x and y differ. So you're given two strings x and y. These are elements of sigma to the n. The distance is the number of coordinates where they differ. So now we have a big set sigma to the n. This is huge, and a metric on it. And this satisfies the triangle inequality. So it is really a metric in the sense that the word. Okay, and so now I'll say what an error correcting code is. An error correcting code, so this is just a definition. It's a subset of sigma to the n. That's it. What the goodness of this error correcting code will depend upon some properties of it, but for now this is just it. A subset of sigma to the n. The errors are there are no errors inside. There's no correcting inside. It's just a set for now. Good. Now, what makes so let C be an error correcting code. So the things that we like, the things that we want out of C to be a good error correcting code. Yes. Oh, right bigger. Okay, I see. Okay. I don't have to start again, right? C is an error correcting code. Good. So the key points about C, key things about C we care about. So the first one is the size of it. And the second thing is how far apart the elements of C are. Okay, so I'm going to define a quantity. This is called the minimum distance of C, the minimum distance of a code C. This is the min over all x not equal to y in the code. So there x and y are in the code and they're not equal, of the Hamming distance of x and y. The minimum distance between some two elements of C. And this is a measure of how error correcting this set is. And why is it that? So yeah, some of you have been to my to some earlier lectures of mine, but okay, I do a magic trick for this. So I need to do this magic trick. I do this even for elementary school students. So yeah, I have to do this magic trick. I can't help it. Okay, so I need a volunteer. Can somebody volunteer? Oh, Jay Kumar, I think that's good. Okay, so yes, okay, good. So I'm going to look away. Please think of an integer between -100 and 100 and show it to everyone. Oh, sorry, you can do it in base 10. Yeah. Okay, oh, good, okay. Now, please think of a real number between -0.1 and +0.1. Give a couple of digits of the base 10 expansion. So if you want 0.12, you would say, oh no, that doesn't work. Sorry, between -0.035, you would say 0.35, something. Okay, and negative if needed. Maybe this way. I don't know. This we are computer scientists. We can. Okay, so I do not know these numbers, as you all know. Can you? Oh, sorry. You can write it. It's okay. Okay, so everyone knows. Yes. Okay. Good. Okay. Now you just have to tell me the sum of what you. What is it? Okay. Okay. Now wait. Your integer was 8. Okay. Thank you. Okay, that's error correcting codes. If you have a far apart space of a well-spaced set of points, these are the integers, and you perturb an element from this set, then even if you give me the perturbed value, I can find what the original value was. Okay, I corrected the error. Okay? This is exactly the same thing. Okay, so here is the observation. If C has minimum distance d, that's the minimum distance between some two elements here, and x is in C, and y is in sigma to the n, such that the Hamming distance between x and y is less than d over 2, then x is uniquely determined by y. I mean, subject to these. There is only one code word that is close to the string y. So the picture is sigma to the n, the elements of C. These are the elements of C. And the distance between any two elements is d. So if I draw a ball of radius d over 2, it will be disjoint from the ball of radius d over 2 near around all these other points. So if you give me a small perturbation of one of these points, I can figure out what this original point. That was the fact. And d over 2 is the fact that in this integer magic trick, we could have perturbed things up to plus minus 0.5. It didn't have to be 0.1. Okay. And this is the error correction part of error correcting codes. Now, to use it, here is the proposed scheme for things. You had something that you wanted to send to someone. instead of sending it, you would choose you would take an error correcting code. We have agreed on this error correcting code, the receiver and the sender. And we would, instead of sending the thing I had, I will pick an element of an error correcting code and promise that whatever I send will be an element of this error correcting code. And the number of different elements that there are in the error correcting code tells you how many different possible data could be sent using this error correcting code. So maximizing the size of the code will let you send more data with n symbols from sigma. So the key question, and this is the most important question of error correcting codes, this is the most important combinatorial question of error correcting codes, and in many settings we still do not know the answer to this. The key question is how big can C be if we know, if we want, let's say, the minimum distance of C to be delta, to be D. That is, it's a combinatorial question. It's also exactly the same question as how many Hamming balls of radius d over 2 can you fit inside sigma to the n disjointly. So can you pack? So it is the same as packing balls of radius d over 2. And this question can be studied in many different settings, in many different asymptotic settings. So n is going to infinity, and we can think of d as 7. We can think of d as square root n. We can think of d as 0.1 n. We can think of d changing as n grows. D being 0.1 n is philosophically significant because it is the fraction of errors that you're correcting, and it's also related to transmitting information on a channel which corrupts 1% or 10% of all errors. So d being a constant fraction of n is especially interesting. Most of this week will be about d being a constant fraction of n, but it's also very, very interesting to study d being other things, and in particular d being a constant is especially, I would say, is the second most interesting regime to study. Okay, so typically d equals delta times n is one asymptotic, or d equals order 1. That's another nice asymptotic. I don't know if I want to say typically. So good setting, yeah, good setting. And I will. So I want to do some simple observations about this problem. How big can C be when you want it to have minimum distance d? I want to play with this problem and just make some simple observations about what kind of things can be achieved. And so I said before already. I said already that sigma can be 0, 1 as one setting, but sigma can be anything, and these are both very interesting settings. Okay, good. Questions about the setup? So this is the basic combinatorial problem. We haven't come into the algorithmic question of how do you get such an error correcting code, how do you use it. In order to use it, you need some things about this code to be efficient, like to be able to refer to the 50,000th element of this code. You should be able to quickly find out what it is. So there has to be some algorithmic things that should be easily doable. So this is one thing that we will talk about in later lectures. But for now, we're just looking at the combinatorial question of how many you can have. Okay, great. So I can keep going this way, right? Or yes? So in this setting, d of delta, d is order 1. Yes, good. So our first observations will give us some insight into what we expect this to be. But yes, the answer will be sigma raised to n divided by, yeah, okay. So if sigma is general sigma, I'm a little this. But yes, sigma raised to n over poly n, something depending on d. Yes. Okay, so let's do the most basic things we can say about this. There's one very simple bound for this problem. I can say it in 3 words. And once I say it in 3 words, you will be able to derive what the bound is. The 3 words are volume packing bound. So what does it mean? It means, it's a packing problem. We have all these balls. They're sitting inside sigma to the n. They all have to fit. That already tells you something. Right? So so this is the volume packing bound. Also called the Hamming bound because it was discovered by Hamming. By the way, this model, yeah, it should have been clear. It is a Hamming metric. Hamming also defined this notion of error correcting code. There is a parallel world of error correcting codes for random errors. And the main person there was Shannon back in the 40s too, just like Hamming. Okay, so the volume packing bound. And the statement is, if C has minimum distance D, then the size of the code is at most the size of sigma to the n divided by the volume of the ball of radius d over 2. I'm using here the fact that the size of a Hamming ball does not depend on where it only depends on the radius. It doesn't depend on where the center is. And that should be clear because, yeah, right, it's clear. Yeah, because you start with a single string x, you want to look at the number of ways you can, whatever perturbation process you did to your string x in order to get nearby all the points around it, that process you could move to other places too. Yes, okay, so we agree. If sigma is 0, 1, then this is, in that case, this bound is the size of C is at most 2 to the n over the volume of the ball of radius d over 2 in Hamming space of this actually be n of d over 2 in 0, 1 to the n. What's the volume of the ball of radius d over 2 in 0, 1 to the n? Let's do it around 0. The Hamming ball around 0 is the set of all strings with at most d over 2 ones, which is n choose 0 plus n choose 1 plus n choose 2 all the way up to n choose d over 2. There are some integrality issues that can help you a little bit. So I will just write that down. So this is n choose 0 plus dot 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 plus n choose floor of d minus 1 over 2. If you follow the details, you can slightly optimize that. And this asymptotically, as n goes to infinity, what is this? As n goes to infinity, this is 2 to the n divided by this whole thing. Yeah, so it depends on d, right? The asymptotics of this depends on d. And in those two interesting settings where d is delta n and where d is order 1, we can talk about what this is. Okay, so I'm now going to tell you what it is in 2 different settings. That's we have size of the code. So we're in, again, sigma is 0, 1. 0, 1. And the size of the code is at most 2 to the n divided by that volume. And it is roughly n to the d minus 1 over 2 is if d is constant. And the asymptotics of this expression as when D is delta n, this is something that, okay, it's not trivial, but yeah, but I mean, it's not complicated either. So if you open up what this means using Stirling's approximation for factorials and you do some stuff, then the fact is that n choose delta n when delta lies in the interval 0, 1. N choose delta n is asymptotic to, or not even asymptotic, is about. I'll say about, there are some lower order things. 2 to the something times n. Some constant depending on delta times n. Plus little o of 1. Good. So this is what I wanted. N choose delta n is 2 to the something times n. That is the asymptotic of the delta nth binomial coefficient sitting here. Why is it this? It's because of some Stirling approximation. What is that constant C sub delta? It is the binary entropy function of delta, whatever that means. So if you know what it is, then good. If not, look it up on Wikipedia. It has some elementary expression, and I don't think I need to know what it is for the talk. So okay, so we won't. And n choose delta n is that, and the sum ends up being approximately the last quantity. And so it looks like 2 to the 1 minus C delta n plus little o. So it is still some exponentially big thing, provided delta lies between, oh, this should have been half. For certain values of delta is some exponentially big thing. For certain other values of delta, it's not. And okay, so it gives us some upper bound on how big this code can be. One particularly interesting setting of this is d equals 3. D equals 3. This is this is an error correcting code that can correct one error. Because d minus 1 over 2 in this case is 1. And in this case, for this case, it says that the size of the code is at most 2 to the n over n plus 1, which is some interesting asymptotic, but I will just use this to compare it with the other upper bound, with now the constructive result that we have, which says that there are codes of a certain size. Okay, so what we did so far was we said that any error correcting code of distance d has some bound on its size. It cannot be too big. And this is just by looking at volume. And now I will try to show you that there is always a code which is pretty big as a function of n in d. Okay, and for that I can even say it in one word. This was a 3-word upper bound. This is now a 1-word lower bound on the size of the code. The word is greedy. So you have a problem, you just solve it without thinking too much, just grabbing whatever you get. So the greedy existence result there exists a code in sigma to the n with minimum distance d with the size of the code at least something. So that's what this bound is going to be. What is the greedy procedure? It is take a point, put it in your code. Now this eliminates a whole bunch of other points from being allowed in your code. that entire Hamming ball, so this was all of sigma to the n. I took a point and the entire Hamming ball of radius d minus 1 is eliminated from being allowed in your code again. Okay, now just take another point. So by greedy is even too strong a word. I mean, there's nothing I'm optimizing. I'm not looking for a point with something better, with something good. I just take any point which is still allowed and put it in. And then it has a ball of radius d minus 1 around it too. And it also eliminates all these points from being in the code. If I'm lucky, the set of eliminated points overlaps heavily with the old set of eliminated points, so I do not lose too many points. But okay, I don't know how to use that. So the number of points that I eliminated may be as big as the ball of radius d minus 1. I do it again and again and again. I will always have some point left over, provided I haven't taken too many points out. So I will say what I get here, and then it should be evident. This is what I'm saying is completely obvious even. Sigma to the n over the ball of radius d minus 1, the volume of the ball. Yeah. Because each point that, I mean, if you have taken out fewer than these many points, then this times the volume of the ball of radius d minus 1 is less than sigma to the n. So there's still a point which has not yet been eliminated. Take that and put it in. So this is the greedy bound. This is d minus 1 here. And okay, and the surprising thing is that we basically do not know a better argument than this in general. So you would think, oh, I can be clever. I will just take the next point to be very, very close to the region of points that have been eliminated so far. And if you do it, maybe you will get a better code, but we do not know how to analyze it. Yes. Oh, yes. Right, good. Oh, so we do not know how to improve this in general. So there are settings where this is the best known thing. Okay, so good. So this is the statement of the greedy existence bound, and by and large, yeah, this is yeah. So in the setting of sigma being 2, the size of sigma being 2, and d being delta n, this is basically the best bound that we know. There are other settings where we know better. Okay, and how does this look, just to know, when d is delta n? Let's say sigma is 2, d is delta n, and d is constant. When sigma is 2 and d is delta n, this is again of this form: 2 to the n, and then it loses an exponential 2 to the c delta n. It is something of this form with a different c delta. So we have some idea of the shape of how big the largest code can be. The c deltas are not the same. This is the volume of the ball of radius d over 2, and that's the volume of the ball of radius d, roughly. So these are quite different. So these c deltas are not the same. Finding out that c delta is maybe the biggest open question of the combinatorial aspect of error correcting codes. Yes. And okay, right. So and in other settings of sigma, there are other settings of d. Yeah, there are a variety of other shapes. So one is the shape that I want to highlight again is when d equals 3, sigma equals 0, 1. Then this says that there exist codes with size of c at least 2 to the n over the volume of the ball of radius 2. What's the volume of the ball of radius 2? N choose 0 plus n choose 1 plus n choose 2. And that's about n square. This is theta of n square. And compared with what happens with our volume packing bound, we know that any code which has distance 3 must have size at most 2 to the n over n, roughly. And this tells us that there are codes with size at least 2 to the n over n square. And this, yes. So we know it's 2 to the n over poly n, and we don't know which one is the right answer, I mean, as of this point in the lecture. Questions? Yeah. Yeah. Yes. Yes. No, this is the best that we know. This is the best that I know, and the proof is that I don't know anymore. or rather, yeah, and we know. I'm pretty sure that's we know. Yeah. If someone knew, I think we should all have heard about it. There are improvements of this of the form poly n times this, but that does not show up in this form. I mean, it is like adding a log n over n to the little of 1. So you can improve this by smaller factors than exponential, but the shape of it is exponential, and we do not know the exponent. No, we do know better for this. We do know better upper bounds. Yeah, using some more clever combinatorics. I'm not going to talk about that, unfortunately, but I can give some words. I will. Yeah. So let me say some words. This is the Hamming bound. There's another bound called the Elias Basiligo bound. Which is which is an upper bound on the side on this, which is related to list decoding of codes. And this is something that we'll see later in the lecture. So we will see list decoding, and after that, once one knows what the word list decoding means, and one knows how the Hamming bound works, yeah, and one has an important ingredient, the Johnson bound, that also will be seen later. Then this gives you a better upper bound on the size of any error corrected. And there are even better bounds. There's something called the linear programming bound, which is even more fancy, which is related to Fourier analysis of Boolean functions. Yeah. There is the delta is d by 2, right? So we are actually applying here. What you will get is this binary function of delta over 2. That's correct. And here we'll get 2 to the n minus binary function of delta. So it is a different function. Yes, that's it. Okay, questions? Okay, so let me, how much time do I have? Okay, great. Oh, great. Okay, so let me also mention now that the setting of d equals 3 and sigma equals 0, 1, we do know the true answer. The true answer is not this. It is that the volume packing bound is tight. These are called Hamming codes, invented by Hamming in his original paper. Hamming codes. There exists C with, I mean, in the same setting. Right? The size of C at least 2 to the n over theta. Yeah, theta of 2 to the n over n. And it's exactly tight with n plus 1 even for certain values. So this is a really, really nice fact. It shows that the volume packing bound is tight. In particular, you can perfectly pack 0, 1 to the n with Hamming balls of radius 1. But such perfect packing or even approximate perfect packing results, we only know in very limited settings. I will mention another word, DCH codes, which do some approximate perfect packing. And these are really amazing codes based on, yeah, these are really amazing codes. Yeah, that's maybe my definition of them. Amazing codes for sigma equals 0, 1. and D equals constant, where they give almost perfect packings of 0, 1 to the n with balls of radius D minus 1 over 2. There's a BCH is a Bose, Chowdhury, and Hokkoguen. Yeah, and these are from the 50s, and they're really, really amazing. I recommend looking them up. Okay, good. So I'm now going to talk about the algorithmic questions related to codes. So this is all I'm saying about the combinatorics of this problem. There's people study it a lot, and it's a really good problem that needs to get resolved eventually there. But yeah. Okay, so algorithmic question. So in order to use an error correcting code, I need to be able to talk about its elements, and I need to talk about its elements quickly. So the first question is to give an example. Give an example of an error correcting code with big size C, at least something, no, big. What we did with the greedy construction was we gave an example of a code, but the procedure to find this code, if you made it an algorithm, would run in time sigma to the n. You take a list of all the sigma to the n code words, all the strings in sigma to the n, and keep eliminating things one at a time. So we want to do these things quickly. So an efficient construction is maybe what I want to say. Efficient construction. But what do you mean by an efficient construction of an error correcting code? It's sitting inside sigma to the n. Its size is exponential. How do you efficiently construct this? I mean, if the final size of the code is exponential, you can't hope to find it in time less than exponential. But it helps to understand the way we're going to use an error correcting code is not to take all the elements of the error correcting code at a time. You're going to say, oh, give me the 50,000th element of it. So what we really need is an indexing of an example. So we want an error correcting code and a way to refer to the ith element of it efficiently. So what this means really is find a C and an algorithm that runs in time fast. So fast for me, I guess I get poly in n and log of the size of the alphabet. That is, I mean, a code word is ultimately specified by string of this size. So this is the standard for what we mean to find it efficiently. So find a C and an algorithm that runs in this much time that maps the size of the code. Oh, okay, I see. I guess 1, 2, 3 up to the size of the code to the code. Yeah, good. Bijectively. This may be my definition of what is an efficient construction of an error correcting code. You should be able to refer to an element of it fast. And then you can hope for running times which are polynomial in n, and n is the length of the size of the code that you're looking at, the size of the code words that you're going to produce, and n is also the size of, some upper bound on the size of the log of this. So you're getting an integer as input. That integer's size is at most n log sigma in bits. So you take that integer and you refer to a particular code. And this is what it means to get an efficient error correcting code. So in this complicated generality, it's hard to imagine what kind of code you would construct. But fortunately, there's a specific family of codes which are automatically very efficiently describable. And we can hope to do it for those codes. So what I want to now talk about is linear codes. So C, so this applies to a very special case. This is when, so if sigma is a finite field, FP or FQ, then you can talk about a linear code. Even more generally, and actually this is what's most popular these days, is FQ to the S. If sigma is of the form FQ to the S, then sigma to the N looks like FQ to the NS. And this is a vector space over FQ. And you can talk about an FQ linear subspace. And C inside sigma to the N is an FQ linear subspace. Then, in this setting, we call C a linear code. So this is the definition, I guess. If all this and C is this. And linear codes automatically, if come with this efficient bijective map. You can refer to elements of a linear code. So first you have to do a little bit of suppose I give you the linear code in your hand. Then you can write down a little bit of information from that code, namely a basis for that code. And then once you have a basis, you immediately have a bijective transformation between, you can index all the elements of your code by specifying which coefficients you give to the basis elements. So linear codes are automatically efficiently encodable once you know the code. Given the code, whatever given means. I mean, to even specify the code, even if the code was specified to you as a big subset, you can then find a basis for it. The basis is now a compactly represented string of length poly n log sigma, and from that information you can take have an efficient bijective map like this. So linear codes are a special family of codes within all codes that have where referring to elements of code of the code is automatically somehow more explicit. So one can take all the questions of coding theory and you can ask, oh, are there, you can restrict yourself to linear codes and then ask, can you find, are there good codes which are linear codes? And as far as we know, the best codes can be linear codes. We do not know that adding the linearity constraint reduces the kind of parameters achievable by codes. So this is, and all the codes that we will talk about are linear codes. So the next problem I want to talk about is decoding. So I did not solve this this problem of finding an explicit error correcting code. I just said that it's okay to focus on linear codes, and we will try to find linear codes that are good. But we don't know how to find linear codes that are good yet. We will, but we're not yet. Decoding. This is another algorithmic question. You are given y in sigma to the n with the promise that delta of xy is at most d/2. Let's say less than d/2 for some code word. And the question is find x efficiently. This is the algorithmic question of decoding. And this is what you need to be able to do quickly in order to use error correcting codes in the manner I described for communication. Because you may have taken your data, you encoded it as a code word, let's say X, it got sent over the channel, some corruptions happened, you received a string Y, which is this perturbed version of X, and your goal is to try to find X. So how do you do this? Well, you have to find it efficiently if you want to use it. And this is the question of decoding. Okay, and efficiently now again means a poly in n and log size of sigma. Since d is the distance of the code, the x is unique. Yes, that's right. But you can also ask this question with you're given a promise that it is less than something which is less than d/2, and then also it's known to be guaranteed to be unique. I mean, there is a question of decode the code from 1/4 the minimum distance errors, and that's also a question one can consider. You don't have to only decode up to half the minimum distance. And you can even talk about decoding beyond half the minimum distance. This is what's called list decoding. And then you have to be ready to either accept any x which is close by or accept all x's that are close by. You have to define the problem. Okay. And what this will do is it will, so in the picture that we have so far, we're missing one piece. So what this will do is it will find the nearby code word. Finding the nearby code word is not the same as finding your original data, right? There was a transformation. You have your data, you convert it into a code word. The code word gets transmitted and gets corrupted. Decoding will find the nearby code word, but then you have to go back to the data. So actually what you really wanted in specifying the code, I mean, you also need the one last transformation, which is taking a code word and giving you back your original data. That's the last piece of this whole thing. Yes. Okay, so for linear codes, since it was, if your map, which is the bijection, is specified by a basis, you can do both directions very easily. So I'm not going to talk about this this issue anymore. But yeah, so for linear codes, finding an explicit construction of the code, finding an explicit linear code automatically solves both the data to code word and code word to data problem. And decoding is the more difficult problem. Okay, good. So now, okay, so I'm going to give you a couple more examples of algorithmic questions that arise. These now we will go to in the direction of local testing and local decoding and things like this. This is what high dimension expanders famously solve, and we will see by the end of the week. So I'm going to start moving towards that. So before that, let me introduce some words that maybe I should have done it before. So let C be a linear code. Okay, so C is a subset of maybe fq to the s whole to the n, right? So sigma was fq to the s. Then there's the dimension of C. The dimension of C is, okay, I'm going to call this K. So let K be this. And this is the number, this is the number of FQ information symbols in C. That is the amount of information, that's the number of F query symbols that you need to specify in order to specify an element of the code. This we'll call K. And then the rate of C is defined to be K over S, or maybe K over S divided by N. Or maybe K divided by Sn. Yeah, that's better. Yeah, K divided by Sn. And it measures, I mean, FQ to the Sn is the space in which the code lies. K is the dimension of this. Sn is the dimension of this. K over Sn is some fraction. It lies between 0 and 1. And it measures how big the code is in some logarithmic way. This is called the rate. S is usually 1. That's how S was 1 until 1995. Then after that, S started becoming bigger. This is maybe 1992. Yeah, S was 1 until 1992, and then people started exploring these other codes. But yeah, so a lot of classical definitions do not have an S. So if you're looking outside, you may not find them. But in this week, you will see lots of S's. Okay. Right, and then our encoding map. Encoding map is a map E is from FQ to the K to T is the bijection. And it's a linear bijection. Once you have a C, an encoding map is an explicit choice that you make after you have the code. And there's the code, which is just the set of vectors, and there is the choice of a basis for C, basically, which does this. So, and some algorithmic questions require an encoding map, and some of them don't. So it's nice to separate the code from the choice of the encoding map. Okay, so there are some more modern questions that people study. These are called local testing and local decoding. We already saw what decoding is. Local decoding is somehow an even sparser version of this, where one doesn't even run in polynomial time, one runs in even sublinear time. In local testing, here we're testing if a given string is close to the code or not, and we're doing this also again quickly. So I just want to mention there's something called global testing, which is easy for linear codes. Global testing, given y in sigma to the n, is y close? Oh, so is y in? So this is actually not even testing. Sorry, I take that back. Just checking membership. Is y in C, and this is easy for linear code. Because of FQ linear algebra, we just check if y is in that subspace. We have already specified the linear code using a basis, so we can do it. Okay, so now I'm going to give you this definition of local decoding and local testing. And then I'm going to wrap up by giving you an example of a nice code if I have time. Do I have time? I have 3 minutes. 3 minutes. Oh, okay, good. I'll take 7 minutes. And maybe the example of the linear code I know Mrinal is going to use. So I better give that first. So let me give you an example. This is the best code of all. The best code. This is a technical term. These are called Reed-Solomon codes. They're very, very famous. It's based on elementary algebra. And from some point of view, they're actually terrible. But there is a point of view which makes them really, really nice. And I will tell you this now. Okay. So we are in sigma equals FQ. So we've chosen our alphabet. You think of your favorite prime, 17 maybe. It is a code over sigma equals FQ. And the terrible thing is that N is now going to equal Q. Okay, so we have listed list FQ to be alpha 1, alpha 2, up to alpha n. N is Q, so we've listed all the elements. And the code word C is P of alpha 1, P of alpha 2, P of alpha n, where P of x in FQX is a polynomial of degree at most. I have to pick a number, so I will pick. Okay, it's gone. Oh, okay, K, fine. I'm just less than K, fine. No, less than or equal to. I'm sorry, I can't help. Okay, we have taken polynomials of degree at most K and evaluated them at all the points of the field. We treat this as a vector of length n. We have all these evaluations. We have specified the order in advance, and this is the code. The size of the code is, there are K plus 1 coefficients required to specify this polynomial. So it is, you specify the Q to the K plus 1. C is linear, because if you take two polynomials and you add them up, their evaluations add up. And the dimension of C is K plus 1. And okay, this is called the Reed-Solomon code. And what is its main property? Is that it has distance. This code has distance. C has minimum distance at least n minus k. Why? If you have two polynomials of degree k, how many values can they agree on? If they agree on some number of values, then their difference is 0 at that same number of values. The difference is a non-zero polynomial. Therefore, it is a non-zero polynomial, you know, cannot have more than degree many zeros. It's a non-zero polynomial of degree at most k. So they're at most k 0. So they're at most k points of agreement. So because degree k polys can have, these are all univariate, have at most k points of agreement. Because of the fundamental theorem of algebra. And so this is our first example of an interesting code. A good way to set things up is maybe k equals 0.1 n, and which is, again, I remind you, is k is 0.1 n. And so in the asymptotic, how does this work? So there's something very unnerving about this, which is that I wanted codes over a certain alphabet sigma. So, but this is going to give me a code of length q. Q is determined by sigma. The longest code you can get out of this is only sigma, because the number of evaluation points you can get is at most sigma. So this is a code over FQ of length at most Q. So it does not give you anything at all. So it's, if you want a large code, you're not getting growing codes. You're not getting codes with n going to infinity over a certain alphabet. So in some sense, this is a completely useless code because it gives you only one particular code for every alphabet size. But there's another point of view which makes it really, really useful, which is to let n grow and be open to the fact that when you're dealing with codes of length n, you've changed the alphabet to something sigma depending on it, sigma sub n. And from that point of view, which is a very strange point of view, because what is this channel that, when I come with 10,000 bits of information, it is suddenly ready to accept 10,000 array symbols. Yeah, so this is a, yeah, so, but this is a really, really good code. So if we view n, sigma as changing with n, this gives us codes with rate k over n and distance, minimum distance. So there's minimum distance and there's relative minimum distance. Relative minimum distance is just the minimum distance divided by n. So I will say that relative minimum distance, n minus k divided by n, which is 1 minus k over n. And this is rate k over n, and so the rate r is k over n, the minimum distance, the relative minimum distance, delta is 1 minus k over n, which is 1 minus r. And this gives us the trade-off rate. So these are codes with rate and with r plus delta equals 1. And this is a really, yeah, so this turns out to be optimal rate versus delta trade-off. This is called the singleton bound. Singleton is the name for person. Right. So these are codes. They're over a changing alphabet. Ah, yes. Good. Good. Yes. Good. 1 plus. So we achieved it with. Oh, this optimal is asymptotic. Oh, yes. Good. Oh, that's. Right. My cheat is that k means two things here. K means correct. K was dimension versus k versus degree of the code. Yes, that's how I cheated. Yes, right. Okay, this is asymptotic. There's a plus 1 over n sitting somewhere here to make this correct. Yeah. Okay. My dimension was k once before, and later I made it k plus 1. So that's how I cheated this. Okay. So these are Reed-Solomon codes, and viewing them as codes over a large alphabet is very, very useful. It helps you get codes over a fixed size alphabet by viewing it this way. So okay, great. So I guess I'm out of time now, but yeah, so Reed-Solomon codes will show up again in the next lecture, and they're the basis of many, many constructions of codes of very, very neat properties, in particular, yeah, with good rate and distance trade-offs. There is another school of thought that produces codes called which comes from expander graphs. We will see those in future lectures, and we'll see, and these underlie the locally testable codes that we'll see at the end of the week. Okay, great, thanks.